All right, guys, so we're in the last section of our physics unit here. This is technically called the dynamics part of the physics unit. The idea of dynamics is we've been spending this entire time throughout physics talking about how things move, like how they accelerate, how they change speeds, what uniform motion is, how we can calculate how fast something's moving. We've been learning about how things move, but we haven't learned about why things move. And that covers the second half of the physics unit. If you take physics 20, you'll actually get a very similar thing where there's a kinematics, a movement side of things, and then a dynamics, a how things move side of things. All right, so we're going to start things out today with a bit of notes. Luckily, a lot of this is review of stuff that you did actually in grade 8. We just take it a little bit further and kind of start linking things together that maybe you didn't link together when you were in grade 8. So things move because of three kind of factors, three things that work together, and those things are work, force, and energy. All right, so we need to understand what these three things are. They're all highly related, but there are key differences in them that you need to make sure you understand. All right, so when we use the word work in physics, it's got a very specific meaning that's different than how we use it in kind of day-to-day speech. All right, so when I use the word work in physics, what we're talking about is how much energy you transfer to something when you exert some sort of force on it. All right. So work in physics is actually a measure of how much energy something has. Sorry, I should rephrase that. It's a measure of how much energy you give to something when you put a force on it. All right. Energy we'll be talking about a lot. We talked about it a little bit back in biology, but we're going to spend a lot more time on it now. Energy is the ability to do work. And I hate these two definitions, these like side by side. They're terrible. The reason I say that is that they're very cyclical. All right. So when I say work is energy that gets transferred and energy is ability to do this, they kind of are reliant on each other. So what I want you guys to make sure you understand is I want you to think of energy like the amount of basically capacity you have to actually get things done. All right. So think of energy like a pool of resources that you have, okay, like that you get from your food or from actually you get it all from your food through cell respiration. All right, so you have all this energy inside of you, and when you do work to something, what you're doing is you're giving a little bit of the energy that you have to that object. So if I were to push say a boulder across a field, as I push the boulder, I'm giving it energy that my body had. All right. So energy is your ability to get things done, and work is just how much of your energy you had to give up to get that thing done. Okay, so that's how those two things relate to each other. The last one here is force. Force is a bit different, but force is how we transfer energy. So force is any kind of push or pull that an object feels. Anytime I push that boulder, I am exerting a force on it. All right. Anytime I pull something along, I'm exerting a force on it. Okay. So energy is basically all the energy that you have. Work is how much energy you transfer to something when you get something or when you do something to it, and the force is how you transfer that energy. All right. All right, so we're going to break these three concepts down over the remaining part of the physics unit. Today we're going to be talking mostly about force and work, starting in with forces. All right. Now, forces are a concept that Isaac Newton spent a lot of time studying, and he kind of came up with the basic rules for what forces are and how forces work to get things to start moving. And those are Newton's three laws that you've heard about before. So we're going to go over the Newton's three laws again and talk about how they affect us and how they came up with some of the physics that drive the idea behind how certain things move. All right. So Newton's first law, which is also called the law of inertia, is the idea that an object will stay at rest or will continue to move uniformly until it's acted on by an unbalanced force. Right? That sounds complicated, but it's not that complicated. The idea of Newton's first law is that if something is sitting still, it will continue to sit still until something causes it to move. All right? Or if something is moving, it will continue to move at the same speed, uniform motion, and in the same direction, uniform motion, until something causes it to not do that anymore, until something causes it to change speeds or to turn or to stop. All right. And the key thing I want you to hone in on here is that this thing will continue to do what it's doing until it's acted on by an unbalanced force. All right. So when something is moving along, like let's say your car, there are different forces that are acting on it. There's the force of the engine pushing the car forward. There's the force of friction pushing the car backwards. And as long as those two forces are equal, the car will continue to move at the same speed that it's currently moving at. If those forces become unbalanced, as in if the engine becomes a stronger force than the friction of the road, what that's going to do is it's going to cause the car to change speed. It's going to cause it to speed up. If friction becomes stronger than the push of the force of the engine, then it's going to cause the car to slow down. That's actually how brakes work. Right? So in other words, as long as if I have an object like this block here, and I have two separate forces acting on it, if those two forces are pushing with the same amount of force, like let's say both of them are pushing with 100 newtons, and I'm going to say this one here is pushing with negative 100 newtons because it's pushing to the left, then this object is not going to go anywhere. All right? But as soon as I change one of those two values, so if I change this guy here to, let's say it's pushing with negative 50 newtons, okay? Now suddenly this force on the left here is going to be stronger than this force, which is going to cause my block to start moving in this direction here. Okay, so things move based on the fact that forces acting on them become unbalanced. That causes them to change speed, that causes them to slow down, or it causes them to speed up, depending on how the forces have actually changed. All right, Newton's second law is a little bit more complex, and I always find it's the one that students have the hardest time remembering, but it's probably the most important one for us because this is actually what gives us the formula that we're going to be using to figure out how we can calculate force. All right, so Newton's second law sounds complex, but it's things that we understand really intuitively well. These are things that you know, all right? So Newton's second law says that the acceleration of an object is directly proportional to the force applied to it, and then inversely proportional to the object's mass. What that means is that an object will accelerate faster if I apply a stronger force to it, which makes total sense, right? If I push something harder, it's going to move faster. It's going to accelerate quicker. We can write this kind of mathematically. This is an approximation, but it'll get us to our formula. It's to say something like, say, so my acceleration is approximately proportional to how much force I exert on the object. Again, we know that intuitively. If you push something really hard, it's going to move further than if you push it really softly. Okay, and then the second half of this says that the acceleration that an object experiences is inversely proportional to the mass of that object, which we also intuitively know. It is harder to get something heavy to move than it is to get something light to move. So the heavier something is, the less its acceleration will be than something light if I put the same amount of force on them. In other words, again, if I'm going to write this mathematically, it looks something like this, is that acceleration is approximately equal to the inverse of the mass. Okay, so in other words, as mass increases, acceleration decreases. Back over here, as force increases, acceleration also increases. So I find students have a hard time remembering this, but I want you to remember that it gives us our formula, and I usually find that that helps students. So here's a formula that we're going to be using for force. Now, this is a formula that you actually saw in grade 8. There's a unit there where you learn about forces. And so there's the formula is that the net force acting on an object is equal to its mass times its acceleration. All right? So it's a nice, easy formula. It's not as hard as the acceleration formula. Okay, and just to remind you here, so A is acceleration. Oh, don't have a place for it. M is mass. And F here is the net force. All right, so it's a nice, simple formula. Now, this is the formula that we use for calculating forces of anything that's moving. For anything that's falling, or when we talk about the force of gravity, we change the formula just slightly to the one that you see at the bottom here. Fg, as in the force of gravity, is equal to our mass times g for gravity, that negative 9.81 meters per second squared. And that's because gravity always causes things to accelerate at the same rate. So technically, these two formulas are the same. This one here is just specifically applying to acceleration of gravity, that negative 9.81. Whenever we talk about something's weight in physics, this is what we're referring to here. weight in physics is actually a measure of force, not a measure of mass. In mass, we use like kilogram, or whenever we're talking about how heavy something is in physics, we always talk about it as a mass. It's how many kilograms that thing weighs. When we talk about weight in physics, we're always talking about the force of gravity pulling something down. You've probably heard that when astronauts went to the moon, their weight was decreased, okay, because the moon doesn't have as strong of a pull of gravity. So as a result of that, they felt lighter because there was less of a force of gravity pulling them down. So when we talk about weight, weight is always referring to force of gravity. And if you ever see that pop up in a question, that's something you need to understand. And we'll get into a few examples of how to use these two formulas once we get through all three of Newton's laws. All right, before we get to Newton's third law, I want to take one more look at this formula and talk about what we measure force in. Okay, a couple things about force. Force is a vector unit. We've talked about that back when we first introduced vectors to you guys. So we need to make sure we include directions when we talk about it. And the reason that's important is that acceleration is also a vector unit. So whenever we have acceleration, it should have a direction with it. So force should also have a direction in it. Forces really, really rely on making sure we know what direction that force is being applied in. The second thing we want to talk about is what forces are actually measured in, all right? And to figure that out, what we're going to do is take a look at our formula. So our formula, again, is F equals ma. For F equals ma, remember, know that mass in physics, we've always measured in kilograms, okay? Oops, there we go. And acceleration is always measured in meters per second squared. So when we want to figure out what our unit ends up being, we can actually use unit analysis here to figure this out. So really what we're doing in this equation is we're multiplying kilograms times meters per second squared. And when you do that math, what you end up with is a kilogram meter per second squared. So technically, this is the unit for force. The thing is, it's a very complex unit, and it doesn't really make a ton of sense. Like, what is a kilogram meter per second squared? I have no basis of comparison for what that could even be. And so what scientists have done is we've actually simplified this down into, we've actually come up with a representation rather than writing this giant unit every time we calculate force. So what we say instead is that we measure forces in newtons. Okay, named after Isaac Newton, who did so much work with forces. So whenever I'm using the term Newton to describe forces, what that Newton actually represents is a kilogram meter per second squared. All right, but we'll just use newtons. All right, and that brings us to the last of Newton's laws, which is one of the easiest ones that I find people remember really well, which is the idea that for every action, there is an equal and opposite reaction. Okay, and all that really means in physics is that any time that something exerts a force on something, so let's say I exert a force on an object, that object also exerts a force on me. And it turns out that the two forces that we're exerting on each other are equal, just in opposite directions. Which sounds kind of weird, like if I push on a ball, the ball also pushes back on me. But it makes sense when you actually think about it, because if I, when I push a ball, it takes a bit of effort for me to do that. And when that effort that I'm having to overcome is the ball pushing back on me. In other words, it's easier for me to move my arm when I'm not pushing a ball than when I am pushing a ball. And what I'm feeling, that resistance, is the ball pushing back on me. It's kind of a weird analogy. I think the best way to think of it is in terms of any kind of contact sport, like football or rugby. And I coach rugby, so that's what I'm going to talk about. In rugby, one of the things that people are always worried about before they start playing is that you don't wear any pads. And the reason they're worried about that is that when you tackle somebody, you're going to feel it, right? So if I tackled you, as an example, you would feel me come into you and tackle you, right? But I would also feel the impact of myself colliding with you. So I would exert a force on you as I tackled you, but you would exert a force back on me as we collide with one another. And so the idea here is that every time two things push, or something gets pushed, both things actually push on each other, all right? And so the only reason that anything's actually able to move is because things weigh different masses. So example, if you go and you push on your wall, you're exerting a force on the wall, but as you push the wall, you're the one that moves back. The wall won't move anywhere. And it's because the wall is exerting an equal force on you as you exert on it, all right? There's no math on this one, which is kind of nice. All right, let's look at some example problems using Newton's second law, looking at that F equals ma formula. All right, so we're going to do a couple example problems. These are all on page 3 of your new booklet at the top there where it says model, right? So the first one here says a trailer with a mass of 300 kilograms is pulled forward by a truck and accelerates at a rate of 4 meters per second squared east. Calculate the total force required to produce this acceleration. All right, so as usual, we're going to write down what we know and what we need to find out. All right, so this problem is giving us a few things. It's giving us the mass of this object, which is 300 kilograms. And it's giving us the acceleration, which is 4.00 meters per second squared east, so it's positive. And then it's asking for force. All right. So this is a nice simple problem. It's already kind of solved the way that we want it to be. So all we're going to do here is use our formula, F equals ma. Our mass here is 300 kilograms. Ooh, geez. 300 kilograms, there we go, times 4.00 meters per second squared. Okay. When I multiply those together, I'm going to get 1,200 newtons. Okay, remember that Newton is the unit for force. And then as per always, we're going to check our significant digits. Here I have 4 digits, but both of my original numbers had 3. So I'm going to need to round this. And to do that, I'm going to have to use scientific notation. So I'm going to rewrite this as 1.20 to give me my 3 significant digits times 10 to the power of 3 newtons. All right, that's it. Nice and simple. Oh, I almost forgot. I would have got in trouble. Last thing on this one is that I forgot to put a direction, right? It gave me a direction in the problem, so I need to have a direction here. This n, remember, is newtons. It's not north, okay? So because this thing was accelerating to the east, I need to make sure I include that E as part of my answer. All right, taking a look at our next one. This time we have a stuffed monkey with a mass of 30 kilograms and it's in free fall, all right? In a vacuum where there is no air resistance. Now that's important for us to note, all right? And for now, always assume that there's no air resistance, and we'll see it in the next problem. Air resistance actually works opposite to gravity. So whenever gravity is pushing something downwards, the air is pushing back upward. That's why we slow down, or why why paper drifts slowly to the ground. It's because the air resistance is keeping it up in the air just a little bit. Gravity is stronger, which is why the leaf eventually, or the piece of paper eventually falls to the ground. But the air resistance also exerts a force, and we'll see that on the next problem. But in this one, there is no air resistance, so we're just going to assume this thing is following with the acceleration of gravity. All right. So again, looking at what the problem gives us, it gives us a mass of 30.0 kilograms. Okay. It's giving us it's not telling us the acceleration, but because this thing is in free fall, we know it's negative 9.81 meters per second squared. Oh, geez. Squared, there we go. And then it's asking again for what is the force of gravity? What is the downward force acting on this object? All right. So we're going to use our formula F equals mg. All right. It's the same as F equals ma. We already know our acceleration. We're just using gravity, which is why I use that formula, but really it doesn't matter. Okay. I'm going to plug our numbers in. So my mass is 30 kilograms. Gravity is always negative 9.81 meters per second squared. Okay, and when I multiply those two things together, what I get as an answer is negative 294.3 newtons. All right, which means I'm going to round this, or when I'm going to take a look at my significant digits, I should have 3 because both of these had 3 digits in them. Right, so my final answer here is going to be 294 newtons, and I need to include a direction, which should be down. Okay, this question here is a little bit tougher, all right? And with this one, I find it kind of helpful to draw a diagram, so I'm going to do that before I solve it, all right? So what we have here is a coconut with a mass of 3,000 grams. It falls out of a tree and experiences a force due to air resistance of 15 newtons, okay? Then it says is determine the net force acting on the coconut. So what's happening here is actually there's two forces working on the coconut at the same time. I have air resistance, which is 15 newtons, pushing the coconut upwards, and then I have gravity pulling the coconut downwards. And when it says calculate the net force, what it wants to know is what is the overall force acting on that object. As in, when I take those two things and I cancel them out, what am I left with, and in what direction is that force acting? All right. So what we're going to do here is, just so you get an idea of it, I've got this coconut, okay, and it's getting pulled downwards towards the ground by some force of gravity. I don't know what that is yet, okay? And then I have my air resistance, so the force, I'm just going to write force of the air, is 15 newtons. I'm trying to write small and it's not working. There we go, 15 newtons. Okay, so what's happening is when it wants to know what is the overall net force is once these two forces cancel each other out, what am I left over with? We know that the force of gravity is going to be stronger, so we just want to know what is the total overall force once gravity and the net force have acted. All right, I'm just going to clear this out of here and we're going to solve this question. So here's what we know. We know the mass of this object, and I'm going to convert grams into kilograms here. We should always use kilograms when we're solving this, never use grams. All right, so I'm going to convert this to 3.000 kilograms, okay? Keeping the significant digits correctly. I know that the force of air resistance, I know it just looks like fair, but work with me here, is 15 newtons, okay? I know that the acceleration due to gravity is negative 9.81 meters per second squared. And what I don't know is the force that gravity is pulling down with. And I also don't know what the net force is. Okay, so I have a lot of forces here. And what we're going to have to do to solve this problem first is to find the force of gravity pulling downwards. And then once we know that, we're going to add our two forces together to figure out the net force. All right, so our first step here is to find the force of gravity. So we're going to use our Fg is equal to mass times gravity formula. Okay, so that's going to be equal to 3.000 kilograms times negative 9.81 meters per second squared. Okay, it's important to keep that negative in there because the force of gravity is going to be a negative force. And I did say we're going to add our two forces together. So it's important that we keep a negative there. When I multiply those two things together, what I get is negative 29.43 newtons. All right. So gravity is pulling downwards with a force of 29.43 newtons. The air resistance is pushing upwards with a force of 15 newtons. So now to find my net force, what I'm going to do is add these two forces together. All right. I'm going to add the air resistance plus the force of gravity. So when I do that, I'm going to go 15 newtons from air plus negative 29.43 newtons from the gravity. And when I add those two together, what I get as an answer is, and I'm going to use the right significant digits here, is 14 newtons down. Okay? When I add those together, I get negative 14 point something, but we're going to round. All right, so because I got a negative, that's how I know that the overall force is going downwards. If the force wasn't going downwards, that means this coconut's going to start rising up in the air, which we know isn't going to happen. Okay, so that's how we find net force. We add all the forces we have together. Okay, here's the last force question we're going to do before we talk about work. And this one I wanted to show you guys so that we can rearrange the formula. If you're somebody that got a printed copy of the booklet, I actually changed this question from what I had. Those of you who are just downloading it offline, you have the up-to-date one. All right, so if your question doesn't quite look like this, you may need to make some changes, but overall question 4 on page 3 should look like this. Right? So your bicycle has a mass of 9.10 kilograms. You apply a force of 22.5 newtons south to the pedals. What will the average acceleration of the bike be? Is what that should say, but that's okay. So in this question, what we know is our mass of the bike is 9.10 kilograms. Okay. The force that you apply, because it's going to the south, is negative 22.5 newtons. And what it's asking for is what is the acceleration. All right? Our formula is F equals ma, but now we're trying to rearrange it to solve for A. So what we're going to do is, because we always want to undo what's happening to the variable that we want, and right now we're multiplying our variable by m, we're going to divide this side of the equation by m, and we're also going to divide this side by m. Mass cancels out on this side, and so what I end up with is that, and I'm just going to write it the correct way, is that A, acceleration, is equal to my force divided by my mass. All right. One easy tip for you guys to remember how to rearrange this formula is the only ways to rearrange it, it's always going to be force divided by something. All right. Kind of like how with the V equals D over T formula, it's always distance divided by something. In this case, it's always going to be force divided by something. All right. So then I'm just going to plug the two numbers that I have in. All right. So my force here is negative 22.5 newtons. The mass is 9.10 kilograms. And when I do that division, what I get in my calculator is negative 2.47 meters per second squared. And I don't want that negative there, so I'm just going to rewrite this as 2.47 meters per second squared to the south. Okay, I'm just going to double check my significant digits. I have 3 significant digits in my answer. Both of my original numbers had 3 significant digits, so I'm done. All right, so that's it for force for now. Let's take a look at our second concept, which is work. Work is really similar to force. Like I said, remember the work is the amount of energy that you transfer to something when you push or pull it. And the way that you transfer that energy is through forces. So these two things go really nicely hand in hand. So work, remember, is whenever a force moves an object over a distance, we do work to that object, all right? And we're pretty picky about work in physics. Work only has certain conditions that need to be met for us to say that we actually did work to something, all right? So the 3 conditions are what's on the screen here. We only do work if a force is actually applied to an object. So if something moves and you didn't exert a force on it, you didn't do any work to it. That object is moving because some other force is acting on it, but not one that you did. All right. Work is done to an object only if that object actually moves. So if something moves, then we know it gained energy. So if I exert myself and I push as hard as I possibly can on the wall of my room and that wall does not move at all, then technically I have not done any work to that wall. All right, I haven't achieved anything, so therefore I didn't do any work to it. I might have used a lot of force to do that, but I didn't move it, so I didn't actually accomplish anything. I didn't do the work that I wanted to do. All right, and then finally, the direction that object moves and the force that I'm applying have to be in the same direction. Okay, in other words, if I push something off a ledge, when I push it, I'm doing work because I'm pushing it and it's moving in the same direction. But as soon as it drops off that ledge and starts falling towards the ground, I am no longer doing work to it. Even though it's moving, all right, and even though there is a force acting on it, it's not a force that I did. Okay, so the force and the movement need to be in the same direction. So a couple of cases where you might think you're doing work, but you're not. This first case, imagine riding your bike and you're going downhill and you stop pedaling. Okay, when you are not pedaling your bike, you are not doing work, even though you're moving. Okay, gravity is what's doing the work there. Okay, we've already talked about, if you push on something and it doesn't move, you're not doing any work to it, like the wall, that sort of thing. And then in the last case, another good example of when the force and the work are not in the same direction. Imagine you're carrying a whole bunch of textbooks, like really heavy textbooks, and you're walking around with them. While you're walking, you're not doing any work to the textbooks. Okay, I should say your arms aren't doing any work to the textbooks, okay? Even if it's a strain to hold them, even though they're so heavy, your arms are exerting an upwards force on the textbook, but the textbooks are moving forward. So it's actually your legs that are applying a force to the textbook, not your arms, okay? Just so that happens. And just remember that work is always a transfer of energy. Whenever something gains energy, it's because work has occurred to it. Whenever something loses energy, it's because it did work. So basically, you get a bunch of energy from your food, and then you go about your day and you do things. You do work to doors as you open them, or you do work to, pedal your bike or whatever it happens to be. What's happening is you're losing energy, and the object that you're pushing is gaining it. So whenever there is a change in energy, that means that work has been done. All right, just like force, we have a formula that goes with work, and this is actually a formula that you would have seen back in grade 8 as well. The formula is this here. It's another simple one, which is great. All right, so W here is work, okay? Because work is a measure of energy, we measure work in joules. Okay, joules are always the unit for energy. It doesn't matter what type of energy it is. It's what we measure it in. We'll take a look at that unit again in a second. Okay, F here is how much force you applied. Okay, and again, that's measured in newtons like always. And then D here is distance, okay, which is measured in meters. All right, so in order to calculate how much work you did to move something, we need to know how much force you applied to it, and then we multiply it by how far it actually moved. All right, so let's take another look at the unit here, kind of like how we took a look at the Newton and what a Newton actually is. I want to explore what a joule is as well. All right, and we can do basically the same thing that we did when we looked at newtons. I'm just going to clear some of this stuff out of my way here. There we go. All right, so let's take a look at our units, right? So force, like we know, is measured in newtons. And we're multiplying newtons times distance, which is measured in meters. So technically work is, or joule could be considered a newton meter, newton times meters. But remember that newton is also a complex unit. Remember, if we think back to what we talked about before, newtons are the same as a kilogram meter per second squared. And we're multiplying that times meters. So what work technically is a kilogram meters squared, because these two things get multiplied by each other, divided by seconds squared. And because scientists are lazy, and because this unit doesn't make a whole lot of sense on its own, like what does a kilogram meter per second or meter squared per second squared mean, scientists have simplified this over time to just be a joule. Joule is measured with a capital J. It is named after the scientist Joule, who spent a lot of time working on energy and what energy is. And energy is not a vector unit. So we do not need to worry about direction at all when we're calculating work. Okay, and it's really important. The idea is, with the reason we don't with work, even though we're using forces for it, is that when I give an object energy, it either has energy or it doesn't. Okay, it doesn't matter if that energy is to the east or to the south. That's not an actual thing. It's just, does that object have energy, and then how much does it have? An object can lose energy, which is the only case where I'd ever get like negative energy, is if its energy dropped. Its energy, the amount of energy it had dropped, but that's a really rare case. All right. So our unit here is joules. A joule represents a kilogram meter squared per second squared, and it's never vector. We don't need to worry about any negatives. All right. So let's take a look in our books at how to use this formula. So we're on page 4. We're going to do the first 2 questions, and then I have one more that's not in the book that's a little bit trickier. All right, so our first question here is a nice simple one. It says, if you push a coffee table 5 meters across a room with a force of 55 newtons, how much work did you do to the coffee table? All right, so looking at this, we know the distance is 5.00 meters. We know our force is 55.0 newtons. We don't care what direction, because work doesn't have a direction, and we're trying to find how much work we did. Okay, our formula is work is equal to force times distance. It's already solved for work, which is what we want, so we don't need to do any formula rearrangement here. So I'm just going to plug my numbers in. My force was 55.0 newtons. My distance was 5.00 meters. And when I multiply those two things together, I get 2,000. Sorry, I'm just looking at my notes, and my notes are wrong. I get 275 joules. All right. And so looking at that, I check my significant digits. I have 3 significant digits in my starting numbers, and my final answer here has 3 significant digits. So I am good. Sorry, I just took another look at my at the booklet. The booklet uses 2 significant digits in the problem. If you haven't looked, it says 5.0 meters and 55 newtons without the 0.0. So your answer in the booklet would have 2 significant digits. The question that I have in this had 3. So the answer key is actually correct. Just a little bit of a difference in the question from your booklet to this. Sorry about the confusion on that. All right, my next one here. So we've got a ball that is hit with a force of 365 newtons. The ball travels a distance of 16.0 meters. How much work was done to the ball? Nice, easy question again. All right. So we have our force, which is 365 newtons. We have my distance, which is 16.0 meters. And we're trying to find work. All right. So work is equal to force times distance. My work here, 365 newtons, times my distance of 16.0 meters. Okay. Again, I'm just going to multiply those two things together. When I do that, I get 5,840 joules. Okay. That would be my final answer, but I have to check significant digits. I end up with 4 significant digits here. Both of my original numbers had 3 digits, so I need to round this to have 3 digits. In order to do that, I need to use scientific notation. So I'm going to change my answer to 5.84 times 10 to the power of 3 joules. All right, done. No directions needed. Great, I love it. Okay, I wanted to do this last one. This is not in your book, but this is the showing you the hard questions that come with work and force. The two questions, or those two formulas on their own, are really, really easy. There's only a couple ways to rearrange them. They're not terribly difficult, but the two formulas can actually link together because both of them have force in them. And so I sometimes have what I call a two-step problem where sometimes I need to calculate force using the work formula so that I can calculate acceleration using the force formula. All right, so this is an example of that. We're going to go through it. It's not terribly difficult, but sometimes it's hard to realize how you're supposed to go about the problem. This is where writing down what you're given in the question and what you need to know really pays dividends for us. Okay, so here we have a car with a mass of 860 kilograms. It gains 72,485 joules of energy as it accelerates. If the car traveled a distance of 55 meters during this time, what was its acceleration? It sounds like a lot's going on here, so it's nice to break it down and just say, what do we know and what are we trying to find out? We know that our mass is 860 kilograms. Okay, that's easy. We know that the work that was done to this car is 72,485 joules. Now I want to talk about this for a sec. This question doesn't say that this car, had this much work done to it. It doesn't use the word work, but it gained this much energy. Remember that work is a measure of how much energy something gained or lost. So this car gained that much energy. That's how much work was done to it. All right, so keep that in mind because it's not always clear in the question whether it's talking about, it won't always say, oh, it had this much work done to it. It will say it gained this much energy. Or sometimes I might be talking about the person. I say the person lost this much energy while pushing something. All right, and you need to realize that any change in energy is the amount of work done. Okay, I mean, the big hint here is really that it's in joules. That's going to be work. Okay. Next, it says accelerates. Cool. We don't know what its acceleration is. That's what we're trying to find out. So I'm going to write that in here. I don't know acceleration. It's what I want to know. Okay. The car traveled a distance of 55.0 meters. Perfect. That's everything the question is telling me. I don't know anything else. There's nothing more I can read into the problem. It's not like it started from rest or it dropped and you have to kind of pick up on clues. It does not tell me anything else. And the problem I have is I have no formula that I know offhand that links mass, work, and distance to find acceleration. All right, those things do not come together. I don't have a way to go from work to acceleration in just one formula. We have not found a formula for that, and if there is one, it's a very complex formula. Okay, but what I do know is I know that to find acceleration, we have two formulas that do that. We've looked at two of them this year. We have acceleration is VF minus VI over T, okay? And we have F equals MA, which I can rearrange to A is F over M, okay? So I'm just gonna erase that first one. So we actually have two ways to calculate acceleration that we've learned, okay? So what I wanna do is figure out, okay, of these two formulas, which one of them might actually be of some help to me, okay? This formula here, I am not told a single thing about initial or final velocity or time in this question. So this formula is definitely out. Okay, I don't have any information that I need to use that one. This formula over here, I don't have the force, but I do know mass. And I have everything I need to figure out force, okay? So if I could figure out the force here, what that means is I could then use that to find acceleration, all right? So this is what makes these problems tricky, is you kind of have to figure out an answer in a very roundabout way, all right? So in other words, we have to find the force in order to find the acceleration, all right? We do know, we have our work formula here, which is W equals FD. And if I use this formula, because I have distance and I have work, I could find force. And once I know force, I can find acceleration. So what we're going to do is we're going to rearrange this formula here to solve for force. So what I have to do to get that is to get F by itself. I'm going to divide this side of the equation by D and this side as well. We cancel out over here, okay? And what I get left with is force is equal to work divided by distance. My work is 72,485 joules. My distance is 55 meters. And when I do that division, what I get in my calculator, once I pull my notes up, because I didn't think to take them out, is 1,317.9 newtons. Okay. Now, my number of my calculator is a little bit more than this. It actually has more significant digits. I just didn't write them down. It's important to keep it in your calculator though. Okay. When you do the math, don't round until the end. What you write down on the sheet may be different than what you keep in the calculator. So in my calculator, I left this number as it was, but all I wrote down was the 0.9 just to save myself some space. So we're not done yet. I'm just going to zoom out a bit here. So we're not done yet because we haven't found acceleration, but now we have everything we need to find it. All right. So I'm going to just change colors here so we know we're talking about something different. So now we're going to use our F equals ma formula and rearranged to our A is equal to F over M. Okay. My force here, not giving myself enough space. My force here is 1,317.9 newtons. My mass from the question is 860 kilograms. And when I do that division, what I get is 1.532 meters per second squared. I need to round it to have the correct number of significant digits. In my original question, this has 3 digits and this has 3 digits. So this should have 3. So I'm going to round this to 1.53 meters per second squared. The question didn't say anything about a direction, so I'm not going to include a direction. So that's it for the notes today. I just wanted to take a second because I didn't go through how to rearrange or for all the different rearrangements these two formulas can have. So I thought I'd put them up on the screen here. They're nice and simple to rearrange. With the force formula, whenever you rearrange it, remember you're always dividing the force you have by the other number you're given. Okay, so notice how force is on top in both rearrangements. That's the easiest way to remember this. Okay, the same thing happens with work. On my work side, I get work is force times distance. When I rearrange that for force, I go work divided by distance. Okay, when I rearrange for distance, I go work divided by force. So the easiest way to remember how to rearrange these formulas is that whatever the original is, whether it's force or work, we're always going to be doing that divided by the other one that we're given. Okay, so hopefully that helps you guys out. I would take a second to maybe write these down or try and memorize them, but they're really easy formulas to rearrange on your own. If you're the kind of person that likes that little triangle, the triangles work in this case as well. So that's it for today, for this video. Now what I'd like you guys to do is go and do the practice questions on page 3, 4, and 5 of your booklet. The practice questions get really tricky on page 5. Question 16 in particular is a doozy. You have to kind of use about 4 formulas, I think, to solve it. So if you can't get any of the level 3 questions on page 5, don't stress too much. Those ones are super, super complicated, and I will go through them on Tuesday's virtual class. All right, guys, have a great day. I will see you in class.